Hello, student. Welcome back to this topic of virtual lab. So here I am going to explain how the some physics experiments can be done virtually using the simulators. So the government of India has provided many simulators to do the experiments virtually under one umbrella called as the VLab. So to go to that, open the Google, and in the Google, you have to search MHRD virtual lab like this, and then enter. It goes to this virtual lab link. So this www.vlab.co.in is the website for that. And click on the virtual lab. So the virtual lab website is open. So this website is created by the Ministry of Education, Government of India. So this facility is provided to do some experiments virtually, which are not possible to do in our labs. So once you open this website, you scroll down like this, and here you will find the broad areas of virtual labs. So these are the many different areas of virtual labs where you can do some experiments. So there are virtual labs you can do in electronics and communication, or even you can do in computer science. There are virtual labs in electrical engineering, mechanical engineering, chemical engineering, biotechnology is there, civil engineering is there, physical sciences is there, chemical sciences is there. So whichever you want, you can choose, or where in which these categories your experiment falls, that you have to choose. So now we are intended to do some physics experiments. So I am choosing this physical science category. Then this new tab is open. So under this, again, there are subcategories. You can do some virtual labs on mechanics, some virtual labs on basics of physics, like this. Many are there. So now I want to do or demonstrate one experiment on laser optics. So that's why I am choosing this as my selection. So in this way, the laser optics virtual lab is opened, and you can find here. So there are many experiments you can do using the laser source. So out of this, the basic experiment is to determine the wavelength of a laser source using the Michelson's interferometer, which we have to do for the MSc Physics course. So that's why I am selecting this experiment, which is Michelson's interferometer for the determination of wavelength of a laser beam. So that's why I've chosen that. And now, once you select that virtual experiment on this, the tab on this experiment opens. So it's a Michelson's interferometer to determine the wavelength of the given laser. This is the experiment. And once you open it, you can see the different things present here, which are seen. So first, theory, you have opened the theoretical part of this experiment is also given. You can see here. You can see. The aim of the experiment to determine the wavelength of laser using Michelson's interferometer is there. And what are the things required? Theoretical part is also given. For example, here you can see the phenomena of interference is explained with all details. For example, this shows the constructive type of interference where the crest of one wave fall over the crest of another. So the intensity becomes maximum. And here the crest of one wave falls over the trough of another, the intensity goes minimum, so leads to the destructive interference. So in this way, you can find out the theoretical part of interference phenomena, and this theoretical part of this Michelson's interferometer is also given. So all these things you can go through. And the next procedure is here. Procedure is also, click on the procedure, you will get the procedure to do this experiment. First, they have given the procedure to do the real lab. So that part we have to skip because we are not doing the real lab. It's a virtual lab. And here, procedure for performing the simulator experiment is here. Some simple steps are there that you have to follow to do this experiment. So these are the steps. Choose laser selection is there, and switch on the laser source, adjust the mirror to get the clear images, adjust the microphone. In this way, just 3-4 steps are there that you can follow to do this experiment. And these are the observation table which is needed to record the readings from this experiment. These are the details of the list count. I will explain later. So once you gone through the procedure, here self-evaluation is there. Next, self-evaluation means here some questions, multiple choice questions are given, and you have to check whether your answer is right or not. Select all your answers, and lastly at the end, if you press result that shows your answer, how much you answered right. That means you can check the knowledge on this experiment in this section. And here comes the simulator. So this is the important part of this experiment. This is the simulator. So once you click on the simulator, the picture which shows the experimental arrangement for this particular experiment opens like this. So in this picture, what you are looking at is here is there. This is the power source for this laser source. This is the laser source. A power source is connected to that, and here are mirrors are there. This is the mirror. It's another mirror, and at the middle, a beam splitter is there. So that splits the incident beam into two. One goes in this direction, another goes in this direction, and after multiple reflection, again they come back and undergo interference phenomena to make the Newton's ring or interference pattern. So the angle of this mirror you can change by rotating this screw gauge. A screw gauge is connected here. So the extended or expanded view of this screw gauge is like this. And here in this region, you will be seeing the interference pattern formed when the interference phenomenon takes place. So these are the experimental arrangements one to understand. Okay. So after understanding the experimental arrangements, we have to click on this button here on the right corner. One button is there. You click here. So this experiment opens like this, and so controls are here on the right hand side. Controls are given, and the first step is to select the laser. What kind of laser? So you click here. When you click there, you can see the 4 lasers are available: krypton laser, helium neon laser, argon laser, ruby laser, like that. So whichever you want, you can select any one laser and you continue. So I'm selecting this krypton laser, the first laser, and let us see what happens. Once you selected the laser source, next you have to power on the experiment. So the experiment is on now. The laser source is on. You can look at this diagram. You can see the green light coming out of this laser source. So this green light, falls on this beam splitter, and it gets splitted into two. One ray goes in this direction, other ray go in this direction. And when they reflected, when they get reflected from these mirrors, they undergo the interference phenomena, and that interference pattern is observed here on the screen. So this is the extended version of the screen. So what we have to do once the power source is switched on, so here we have to adjust the mirror. So these mirror, you can see here interference pattern is already formed, but it is not clear. To get a clear and sharp interference pattern, we have to adjust the mirrors, these two mirrors. When they become 100% parallel, you will get a sharp image, because in the theory of interference, Michelson's interferometer, you have read that uses the parallelly 100% parallel mirrors. So that's why we have to adjust the mirrors in such a way that the pattern formed in the screen is bright and sharp. You can see here. Now I'll show you. I am moving this knob to change the intensity and sharpness of the interference pattern formed here. So you can move down, you can slide this knob to change the intensity as well as the sharpness of the fringes. You can see here. You see, now it is blurred, get short, again blurred. So leave this adjustment knob to the place where the fringes are sharp. You can see it. So what happens at the position where at the position of the mirror where these fringes becomes sharp, this another knob gets activated. So this is called as the micrometer adjustment knob. So it gets activated. So next step is to adjust this knob, micrometer knob. Main adjustment is over. Now we have to do the fine adjustment by making use of this micrometer adjustment knob. So this micrometer adjustment knob is required to change the interference pattern. So just I will show you what happens if I moved this micrometer knob. You can see here, you see the interference pattern is also changing, and you can look at interference pattern is also changing, and you look at this micrometer reading is also changing in this way. So that happens when we are moving this micrometer adjustment knob like this, you see. And also at this junction or at this point, I will also explain how to take the reading here, because this micrometer reading is very, very important. So as we move this knob, this micrometer reading changes, that we have to note down. Just look at this micrometer, a little bit about this. So this micrometer don't have the errors. It is like a screw gauge. I will show you. You see? You see, at this point, the zero of the head scale and this is the pitch line, both are aligning exactly. So there is no error in this screw gauge or the micrometer. So that's why I don't think about the errors here. Now we have to check what is the least count of this micrometer. You can see here Between 0 and 5 divisions are on the upside and 5 divisions on the downside. So the every division on the upside gives uh, the full digit of the micrometer. That means the first line is the 1 mm line, second is the 2 mm line, like that. So between 0 and 5 mm lines are there, and these down ones are the half digits. So the first line is the is the half of 1 mm. That means 0.5 mm line it is. So it is 0.5 mm. This is 1.5, 2, 2.5. In this way, the scale goes on the this pitch scale. So that we have to note down. What is the least count? Pitch is 0.5 mm. Here this is the value of the first line. Pitch is 0.5, and the total number of divisions on the head scale is 50. 45 plus 5, 50. So the least count is 0.5 divided by 50. That gives 0.01 mm. So in this way, you can calculate uh, the least count of the this screw gas. Now I will come to this point again. Now we have to understand how to take the readings. So when you are moving this adjust micrometer knob, this one, the interference pattern changes. So you have to look at the center of this interference pattern. So at the center of the interference pattern, sometimes a dark fringe is formed, sometimes a bright fringe is formed. So that happens. So when you bring this adjustment knob to the extreme end, you can see here a dark fringe is formed at the center. So this is the start of your experiment. And click on this micrometer knob and use the right arrow mark on your keyboard of the laptop or computer. Then go on pressing it, right arrow mark, and observe at the center. What happens? You will see that, you see, the rings are coming out. The rings are coming out. So you have to count the 20 rings at the center. You have to count the 20 rings. And what is this? What is the micrometer reading for these 20 rings which are coming out? That we have to count. So you can see now, I'll start from beginning. You see, look at the micrometer, it is 0, 0. Now I'll start moving. You see, this is bright fringe is there at the center. Now again dark fringe is forming, bright fringe is there. So in this way, you can either count the bright fringe or dark fringe, whatever it is. You have to count 20 number in this way, and count 20 number in this way by pressing the right arrow mark on the keyboard. You see, you can now it is approximately 20 fringes, and look at the micrometer reading. It shows some 5 divisions on the head scale in this way. And I will move another 20. Just I will show you. I'm counting in this way. It's you see, and now it is nearly 20. Another 10, another 5 micrometer readings is there. So it becomes, now it is at 10. So in this way, use the arrow mark, right arrow mark on the keyboard and press it, hit it, then count the either dark fringe or bright fringe at the center. Better to count the dark fringe. Then and for every 20 fringes, you have to note down what is the micrometer reading on the screw gauge. So that is the point. So in this way, you have to complete the experiment. At least for 10 readings, you should have 10 to 15 readings you can take in this way. Then you can stop. At least 10 readings are enough. And here place the glass plate is there. I am not placing any glass plate in this part because that is used for the second part of the experiment. The first part of the experiment is only to determine the wavelength of the given laser beam. That's why I am not making use of this. So the experiment is now over. You can go down, and in the tabular column, you have to note down the readings. So here I will show you how these readings looks like. Just I will show you. Here is the one thing what I have done. So this is the experimental readings which we have recorded using the simulator. And now you see, this is the first part. Least count calculation I have shown here, which is 0.5, total HST is 50, least count becomes 0.5 divided by 50, it is 0.01, and number of fringes what we have counted is 20 here, and these are the readings. There was no pitch scale reading, 0, 0, 0, 0. PSR means pitch scale reading was 0. And HSR, these are the HSR reading. 5, there was a 5 divisions moved on that scale for the merging or for the emergence of 20 fringes at the center of the Newton's ring. For next 20 fringes count, the HSR reading was 10. For next 20 fringes count, it was 16. In this way, the readings are taken, and least count was calculated using the formula PSR plus HSR into LC as usual. So these are the micrometer readings. And here you have to calculate what is the distance uncovered by the screw gauge head screw for the emergence of 20 fringes, or for the merging of 20 fringes at the center of the Newton's ring that we have calculated here. These are simply the successive difference of these readings. For example, this reading minus this reading gives this, and this minus this gives this, this minus this gives this. In this way, these are the successive differences obtained for the 20 fringes, and the mean distance traveled by the screw means this is the average or mean of all these readings is 0.05 mm. And next, now what I am in last part is to calculate the wavelength of the laser light, which because laser light of the laser source I selected is the krypton, but formula is same whether you are selecting krypton or helium, neon or whatever. The formula is same. The formula is lambda is equal to 2d upon n is there. And D means this mean distance traveled by the screw, that is 0.05. So substituted here, divided by capital N means the number of turns or fringes for which this distance was measured. So it is 20. So 2 into 0.05 into 10 power minus 3, because D is in mm, divided by 20 gives 0.005 into 10 power minus 3 meter, or you can convert this into nanometer. It comes around 500 nanometer, and you can Google it. The standard value of this lambda for krypton is around 520 nanometer. So now for the green line, so it shows that the experiment what you did using the virtual lab, what you did for this determination of the wavelength of the laser light using the simulator is correct. So it is giving nearly the equal value, which is nearly equal to the standard value of the lambda of the krypton. So this is the how you can do this experiment using the simulator. Thanks for watching.